I would like to thank the organizers for giving me this opportunity to speak here. I'm Shaokai Jian from Brandeis. Today I'm going to talk about late time for Neumann entropy and measurement-induced state transition. This talk is based on these papers in collaboration with Brian. So to motivate my talk, let's first talk about thermalization. Traditional wisdom to understand thermalization is to consider the system coupling to an environment. Because we are not able to access the information in the environment, we are going to trace it out. Then the system is in a mixed state. Statistical mechanics will emerge from the description of a mixed state. However, nothing forbids us to include both the system and the environment as an isolated quantum system. Then the question comes to, how does an isolated quantum system thermalize? Experimental improvement over years now can achieve dedicated controls of an isolated quantum system and answer this question. Let's consider quantum quench experiment. We start from a pure state with little entanglement between different sites and evolve the full state under some chaotic unitary dynamics. At late time, it is still a pure state, but the entanglement between different sites will establish. Local observable will look thermal because of the entanglement with the rest of the system. This is an experiment of quantum quench. Figure A, B, and C plot the Renyi entropy of subsystem A with 1, 2, and 3 qubits. As you can see, the Renyi entropy will grow at the beginning and then saturate to a plateau given by the entanglement of the steady state. Figure D plots Renyi entropy of the full system. Because the full system is a pure state at all times, the Renyi entropy will stay nearly zero. This answers the question. The entanglement, the establishment of entanglement between different sites in the quantum state is the key to understand the quantum thermalization. Many-body entanglement is still at research frontier, not only for experiments, but also for theories. For example, it is closely related to information paradox. If we consider entanglement between two black holes, starting from a less entangled state, it will follow a Pape curve, and it will grow at first and saturate to a plateau. In this time, there's no environment, so the Pape curve will not go down, but saturate to a steady state. This has been shown in many important works, including these two groundbreaking papers. I want to emphasize that Pape curve also exists in many body systems, even without gravity duality. For example, we can consider two burning coals instead of two black holes. Suppose they are in a product state between, say, A and A bar. And if we look at the von Neumann entropy of A, it will follow a Pape curve much similar to black holes. This picture is very intuitive, but actually we don't have, actually there is few examples of analytical calculation for Pape curve in many body systems, especially at late time. So the question I want to address in the first part is, can we have a solvable model such that the late time von Neumann entropy can be calculated analytically? And in the second part, I will talk about the transition of late time entanglement entropy. To have the entanglement transition, we will measure the system. Projective measurement decrease the entanglement. M is an example of measurement of a qubit. There are projections to 0 or 1 state. A simple example to show a local projective measurement decrease entanglement is to consider measuring an EPR state, for example. Imagine we have an EPR state between 2 qubits. If we measure the first qubit, the wave function will collapse into 0, 0, or 1, 1. because of the projection. Now, before measurement, the two qubits share log2 entanglement, but after measurement, they share 0 entanglement because they are in a product state. This can be generalized to many-body state. Imagine we have a many-body state with many qubits. If we make full measurement to all qubits, the wave function will collapse into product state between different sites. And the measurement destroy all the entanglement in the system. We can also make a partial measurement to a subset of qubits, for example, a random subset of the qubit. And in this case, measurement only destroy parts of the entanglement. So it is clear that measurement can decrease entanglement, and actually it can lead to a phase transition. Here is the setting for measurement-induced phase transition. We consider a chain of qubits in the horizontal axis, and the vertical axis denotes the time step. At each time step, we apply random unitary to entangle two nearest neighbor qubits, and at long time, these random unitaries can generate a volume law in the system. On the other hand, we also make single qubit measurement between time steps with a finite probability. Then the competition between the random unitary that increase the entanglement and the local measurement that decrease the entanglement will lead to an entanglement transition as a function of the measurement probability. So this figure shows the entanglement entropy of a subsystem A as a function of the length of A. Different curves correspond to different measurement probability. For small measurement, we can see the entanglement entropy scales linearly with the length. The system is in a volume law phase. Increasing the measurement probability above the critical value, the entanglement entropy does not scale with the length at all. The system is in an area law phase. So we realize a transition from volume law phase to an area law phase as a function of the measurement probability. For random circuit model, there is a mapping to statistical models to understand such a transition. But going beyond this, few analytical result is available. So in the second part of my talk, we are going to answer the following question. Can we have a solvable model such that a transition can be demonstrated analytically? So I have raised two questions. Can we have solvable models such that late time or Neumann entropy can be calculated analytically, and such that the measurement-induced phase transition can be demonstrated analytically? I will answer these two questions in the rest of the talk, and the answer is yes. We studied a Brownian SYK model to explicitly calculate the late time or Neumann entropy and the measurement-induced phase transition. This model further shows that, first, the correlations between replicas account for the page value at late time. In particular, they are described by permutations. And second, measurement-induced phase transition coincides with the breaking transition of replica symmetry. So let me start with the first part. People are familiar with SYK model. It describes a bunch of Majorana fermions with 4-body all-to-all random interaction. The side denotes the Majorana fermion. J is a Gaussian variable. So the Brownian SYK model is to replace this quench Gaussian variable by a Brownian Gaussian variable. The variance is proportional to a delta function at time. It means at each instant of time. It is an independent Gaussian variable. So this model can have a random circuit picture, and it will actually reach a hard random ensemble at long time. This model is simpler and solvable. It is also chaotic with Lyapunov exponent given by the coupling, as the temperature, as the energy is not conserved. So to mimic the two burning coals we consider two coupled Brownian SYK clusters, A and A bar. Each cluster has the same number of Majoranas, capital N, interaction within each cluster and the coupling between two clusters or Brownian Gaussian variables. So why we choose this model? First, after integrating out the Gaussian variable, the Green's function is local in time. Namely, it is a single time field because of the randomness. Sorry, because of the Brownianness. It is not like the regular SYK model with quench disorder, where the Green's function is bilocal in time. And actually, this feature makes the model solvable even with multi-contours. Second, this model is very chaotic such that it can take an initial state to a random pure state at one time. Because we know many results about entanglement of a random pure state due to Pape, we can benchmark our calculation. So here we study quantum quench. Our problem, we start from a product state between A and A bar and evolve the state by this Brownian Hamiltonian. We are interested in von Neumann entropy of subsystem A by tracing out A bar. And we are going to use the replica trick. And we calculate the Renyi entropy and take the replica limit n to 1. The initial state is chosen to be the double state. To prepare it, we make two identical copies of the original system. Here, En is the eigenstate of left or right systems. Beta is the inverse temperature. It is convenient to represent Sommerfeld double state by a semicircle, starting from an EPR state and evolve under left and right Hamiltonian respectively. Because we consider a bipartite system, A and A bar, we separate them by two semicircles, and a dashed line between them indicates the coupling between A and A bar. Our strategy is summarized here. We use path integral to represent Renyi entropy. We solve saddle point equation, and then we use saddle point solution to get Onshell action. All right, path integral. This is the definition of Renyi entropy trace of rho A to nth power. Rho A is the reduced density matrix of A. We need to first trace out A bar. And we are going to represent this quantity by a path integral. A schematic plot is shown here. So for A bar, it is traced out. Two semicircles are connected to form a full circle for A bar. On the other hand, there are twist operators inserted in A. So the coupling between A and A bar in the upper semicircle is also between different replicas, namely alpha is coupled to alpha minus 1 in the upper semicircle. Alpha is the replica index running from 1 to n. Real-time evolution can be obtained by complex continuation, so we have a Keltish-like contour for the real-time evolution. For Brownian Hamiltonian, we can set beta to be 0 because the energy is not conserved. So we don't have the circle, but a Keltish-like contour. The twist operator acting on the upper semicircle now act on the backward contour. So we need to insert a twist operator for coupling between A and A bar in the backward contour. The plus means forward field, there is no twist operator. Minus means backward field, where we insert a twist operator, epsilon, which is a cyclic permutation matrix in our notation. In SYK model, we talk about correlation functions between Majoranas because we have n replica to calculate Renyi n entropy. The key quantity here is the correlation between forward and backward contours of different replicas. So alpha and beta from 1 to n is the replica index. X is either A or A bar for these two subsystems. Here we use the black arrow to indicate forward contour and the blue arrow to indicate the backward contour. And we have solutions for A and A bar. This orange G is a simplified notation for this correlation between different contours. We also use this orange line connecting different contours to indicate the solution. Here is an example for replica diagonal solution, where the correlation is within each replica. As you can see, 1 is correlated with 1, 2 is with 2, and n is with n for this replica diagonal solution. But in general, the solution is given by permutation matrices that characterize possible correlation between replicas. Effective action is a function of this correlation. It contains, of course, A and A bar and the coupling between A and A bar. Here, I want to emphasize for the coupling between A and A bar, there is a twist operator, which is again the cyclic permutation matrix. So this coupling between A and A bar actually determines the time dependence in the question. If we use this diagonal solution, if we plug this diagonal solution back to the action, we will have a trace of a twist operator, which is a cyclic permutation. So it vanishes, and it actually leads to a linear time dependence. So this diagonal solution is for the early time Renyi entropy, not for the late time saturation. To get a time independent solution at late time, imagine the solution in A bar is still given by this replica diagonal solution. It is not hard to see that the solution in A, if the solution in A is given by the twist operator itself, we can get the trace of an identity, n times n identity, and this will cancel the time dependence. More generally, if the solution in A bar is given by an arbitrary permutation matrix denoted by tau A bar, the time independent solution in A is epsilon times tau A bar. For this solution, we still get a trace of an identity, and this will cancel the time dependence. So the late time solution is a pair of permutation matrices that are related by the twist operator. For this solution, the coupling between A and A bar vanishes, and the rest part, for the rest part, what we need to do is to evaluate the Fafin. Fafin is from Gaussian integration of Majoranas at each replica when we use the self-energy and the Green's function to decouple interaction. So the upshot is that what really needed to evaluate for Onshell action, since we already have the solution, is the Fafin for both A and A bar. So before I evaluate the Fafin, let's look at, before I evaluate the Fafin for n replica, let's first look at a single replica with Keldysh contour. So this is the action on Keldysh contour. Plus means forward field, minus means backward field. They have opposite time derivatives. And this is the boundary condition at time 0 and time t. The minus sign is because of fermionic field. So we can imagine to hit a state at time capital T to match the boundary condition at time capital T. This state psi will relate the forward fermion to a backward fermion. And this reminds us of an EPR state, where I use psi and chi to denote the Majorana operators for this EPR state. And you can see the similarity between these two equations. The boundary condition at time 0 can be taken care of by taking Hermitian conjugation. This minus sign is because of the I in the definition. So this suggests us to identify the forward field as the psi Majorana and the backward field as the I chi Majorana in the EPR state. This graph represents the identification between contours and the operators. Using this identification, the time derivative for this backward evolution will change sign. So in the action, we have forward for both contours, and this action actually calculates the transition amplitude of EPR state and the Hamiltonian H. Now we are ready to look at n replica. So there are n Keldysh-like contours. Alpha and beta run from 1 to n. Again, the Fabin is equal to the transition amplitude of n tensor product of EPR state. And the effective Hamiltonian here is given by the Onshell action of self-energy. Remember, the Onshell action is a permutation matrix, and for any permutation matrix, there is a cycle decomposition. Namely, permutation matrix can be decomposed into a block diagonal matrix where each block is a cyclic permutation or a cycle. We use L to denote the length of a cycle, and the sum of the length of all cycles is equal to n for both A and A bar. For example, if n is equal to 5 and we have a solution like this, it is easy to see that this solution can be decomposed into 2 cycles. The first one has 3 elements, and the second one has 2 elements. Now, the effective Hamiltonian for a cycle is actually the nearest neighbor hopping between Marianas. For example, for this cycle with length L, if we use the identification between contours and operators, it describes the nearest neighbor hopping between these Mariana operators. And this model is nothing but a Kitev chain. The Hamiltonian describes nearest neighbor hopping between Marianas. And the side index is the replica index. The length of the chain is the length of the cycle. So we map the calculation of Fabin to the calculation of transition amplitude in a Kitev chain. And this can be obtained by going to BDG Hamiltonian and occupying all negative energy state. So here's the result. The first term is from the Hamiltonian, and the last 2 terms are from the overlap between the EPR state and the ground state of a Kitev chain. Again, remember there is a cycle decomposition of permutation matrices for solution of A and A bar. The Onshell action then is given by the summation of contributions from all cycles. And this first term will cancel the time dependence. The second term gives minus 2n log 2, and the last term will pick up the number of cycles in the solution for A and A bar. Recall the solution is given by a pair of permutation matrices. They are related by a twist operator. It is known that the maximum number of cycles in such a pair is n plus 1. If we use this result, then the Onshell action is simply 1 minus n log 2. But we need to consider the degeneracy. There are actually Cn number of pairs which have n plus 1 cycles. Cn is the Catalan number. If we include this degeneracy, we can get the Onshell action. And also make the analytical continuation to n equal to 1 to get the von Neumann entropy. So here's the result for the von Neumann entropy of subsystem A. A few remarks. The first term, the leading term, is because in A we have 2 n Marianas in thermofield double state. And at infinite temperature, each Mariana operator has half log 2 entanglement. So in total, we have n log 2 entanglement. The second term is a 1 over n correction. And it is from this Catalan number. It is actually consistent with correction for a random pure state due to Pape's calculation. So the correction is given by exactly -1/2 when NA is equal to NA bar. And the last correction is from local forming parity symmetry, which I don't have time to go into details. We can generalize our calculation to a chain of Brownian SYK clusters that are coupled by the nearest neighbor coupling and consider von Neumann entropy of subsystem A, for example. The saddle point solution is again a pair of permutation matrices that are related by twist operator. The Onshell action has a factor of LA and LA bar corresponding to the length of these two subsystems. When LA bar is equal to LA, the calculation is same as two clusters. When LA bar is greater than LA, we don't have degenerate saddle point solution. The solution is there is only a unique dominant solution such that in A bar it is given by a trivial permutation, whereas in A it is given by a cyclic permutation. So the number of cycles in A bar is given by n, and the number of cycles in A is just 1 because it is itself a cycle. If we use this result, the Onshell action is simply 1 minus n, LA log 2, because the contribution from A bar vanishes. Then the von Neumann entropy for subsystem A is very simple. The first term is the maximum entropy you can have, and the second term is from local forming parity symmetry, which I don't have time to go into details. Actually, there is still a sub-leading correction from Pape's calculation, but in this case, when LA is not equal to LA bar, such a correction is not included in perturbative large N calculation. So it will be interesting to see how we can get this correction in exact calculation. Okay, this is a brief summary for the first part. We show that the correlations between replicas account for page value for late time. In particular, they are described by permutations. Now let's move to the second part about measurement-induced phase transition. We will use the Brownian SYK chain to explore the measurement-induced phase transition. Without measurement, this chain has a volume law phase. To construct the measurement, we consider actually two Brownian SYK chains. We pair the left and right Majorana for each flavor at each site to a complex fermion like this. Each complex fermion has two states, the unoccupied state and the occupied state. Here is our measurement operator. It contains projections to either unoccupied state or the occupied state, as well as a real parameter S. S is the measurement strength. If S is 0, there is no measurement. If S is 1, this is a projective measurement. When S is between 0 and 1, it is a weak measurement. If we divide the chain into two parts, A and A bar, and look at the von Neumann entropy of subsystem A, we expect there will be a transition from a volume law phase to an area law phase as function of the measurement strength. Because when S is 0, there's no measurement, the system is in a volume law phase. When S is 1, the projective measurement will collapse the state into a product state between different sites, and the system is in an area law phase. So let's look at the effect of measurement. Let's consider first, without measurement, the unitary evolution of a single replica. So in this case, the left and right chains just decouple. And the equal time correlation between contours is given by the maximum value because the forward evolution will cancel the backward evolution. And the maximum value is 1/2 because in our notation, Majorana square is 1/2. Now let's turn on measurement, and it is effectively a non-unitary evolution to couple left and right chain. It's like this term because the projection to say the occupied state contains an operator like this. So the effect of measurement is to mildly project the state into the correlated state between left and right chains. And here's the Onshell action. So it's the saddle point solution for a single replica. Theta characterize the measurement strength. So as we increase theta, the correlation between left and right chain will increase as expected in sin theta. But the correlation between forward and backward evolution, forward and backward contours of the same chain will decrease. In particular, the correlation between the contours vanishes at theta equal to pi over 2. So the effect of measurement is to decrease the correlation between different contours. Now we are ready to look at the saddle point solution for this chain. So without measurement, we already know the saddle point solution for LA bar greater than LA. In subsystem A bar, it is given by trivial permutation, whereas in A, it is given by a cyclic permutation. After we turn on the measurement, it will couple the two chains. And as I said before, the effect of measurement is to decrease the correlation between different contours. Theta is the measurement strength. And there's a transition at theta equal to pi over 2, where correlation between different contours vanishes. And this is actually a transition where replica symmetry is restored. Let's look at the bulk action. There are n forward contour as well as n backward contours, and the theory is invariant under any permutation among the forward contours and among the backward contours. So the symmetry in replica space is given by Sn cross Sn, where Sn is the permutation group. Saddle point solution for theta less than pi over 2 correlate between different contours and spontaneously break the symmetry. Because once the contours are correlated, we are not allowed to permute them independently anymore. Then the measurement-induced phase transition is a mechanism to restore the symmetry, because measurement decreases the correlation between contours. So the transition at theta equal to pi over 2 is the transition of replica symmetry restoration. This is the phase diagram. The x-axis is the measurement strength. So for small measurement strength, theta between 0 and pi over 2, the symmetry is spontaneously broken. Whereas for large measurement strength, the symmetry is spontaneously restored. We calculate the von Neumann entropy for these two phases, and we find that symmetry broken phase satisfies a volume law, and symmetric phase satisfies an area law. So entanglement transition coincides with the replica symmetry breaking transition. So the calculation for the von Neumann entropy is very similar. The fluffing can be mapped to transition amplitude of EPR states. But the Hamiltonian now is two coupled Kitev chains, and the coupling is precisely the measurement. To get the Onshell action for arbitrary n and make the analytical continuation to get von Neumann entropy for, say, subsystem A. So the length of subsystem A is LA. So the prefactor is the line tension. If the line tension is finite, it is a volume law. If the line tension is 0, it is an area law. So here we plot the line tension as a function of measurement strength. As we increase the measurement strength, the line tension will decrease from a maximum value to 0. And the transition point is exactly at pi over 2, coincide with the measurement, sorry, the replica symmetry breaking transition. So here is the conclusion. In the first part, we show that correlations between replicas account for the page value at late time, and they are described by permutations. And in the second part, we show that measurement phase transition, induced phase transition coincides with breaking transition of replica symmetry. These results are explicitly shown in Brownian SYK model, but we believe it is in general true. And it is an interesting question to generalize the calculation to other models. With that, I will thank you for your attention.
Questions?
Yeah, I think it's a small comment. Technically, the long-term solution you find, it does not satisfy the boundary condition. So the actual Lagrange solution have some like change near the endpoint by some scrambling effect, but that doesn't change our final answer because this argument about the projection in the middle to the ground state doesn't change. But you should use different Hamiltonian, although they cancel. You shouldn't use this two Fermi interaction. It's like a Q Fermi interaction.
So what is the last part you say?
Right. So when you do estimating, this Hamiltonian, you use a constant sigma, right?
Yes.
That is not correct near the endpoint.
You're right. There will be boundary effect, but this boundary effect has an exponential decay.
Yeah.
And we think it does not change the result because in the end of the day, it is a time-independent solution.
I have a connected probe, maybe more basic question. So you said that there was a replica symmetry, permutation symmetry, but when you connect the various contours to define the regions, you are breaking the symmetry explicitly.
Yes.
So why should we not need to take care of this explicit breaking, and why can you talk about spontaneous breaking?
Right. So right, very good question. So actually, this symmetry is only valid in the bulk. The boundary condition to calculate Renyi entropy explicitly break the symmetry. And we believe that at long-term limit, this symmetry breaking story in the bulk determines the phase, because the phase is the transition in the bulk, not in the boundary. We have the transition, but this transition is on the bulk.
But you mean bulk in time?
Yes.
Yeah.
Yeah, I have a technical question. So in the first part, you computed the Neumann entropy, and you had a leading n log 2 term, presumably coming from some large n saddle. Yeah, I think it's here. Yeah, and then you have extra 1/n effect. So presumably they come from some combinatorics of these cycles. So how much should I trust this 1/n correction? Are there any other 1/n corrections coming from the fluctuations near the saddle?
Yeah, that's a great question. Yeah, that might be correction to that, but the upshot is, well, we get this. So for this Brownian SYK model, it is a Brownian model. So we know at long time, it will reach the hard random circuit. So it basically brings a pure state to a random pure state in the Hilbert space. And there is another calculation by Pape saying that the correction is at least in the large Hilbert space dimension limit given by -1/2. But I agree that if we change the Hamiltonian to like a regular SYK model, the energy is conserved. So it will not reach a random pure state at late time. And there will be presumably other corrections which coming from the fluctuation of the shadow.
Online questions? Okay, not that time. Thanks, Shaokai again.